Hi everyone, in this video we are going to solve one problem. We have studied many things about fundamental property relations, we know Maxwell relations, but how to use those equations to solve any problem of chemical engineering thermodynamics. Here we are going to solve that one problem using those equations. First let me draw expander. According to the problem statement, a real gas is expanded isothermally, that is T1 is constant, that is equal to T2, and initial volume that is given 0.04 meter cube. Here volume is 0.1 meter cube, and the equation of state for this problem is given P is equal to RT upon V plus A upon V square, and A is a constant. The value of A is given minus 50 meter cube per mole square into Pascal. Our objective is to calculate delta H, to calculate delta S. Earlier I have explained about any problem. If you want to solve any problem, you should segregate two things: what are the known parameters and what are the unknown properties or parameters. Here the known parameters are V, volume, and other is temperature. Though I don't know the value of temperature, but I can consider as a known parameter because temperature is constant, and unknown is H and S. Let's start with the delta H. I should write enthalpy. If there is a change in volume, what is the change in enthalpy at constant temperature, because the process is an isothermal. So my objective is delta H over del V at constant temperature. If I am able to calculate the value of this partial derivative, then I can calculate delta H because I know the change in volume at constant temperature. But this is not measurable. We should convert this derivative in terms of measurable. Okay, let's start with the fundamental property relation. You know the property relation of enthalpy, that is V dP plus T ds, and if I write enthalpy as a function of two parameters, that is P and S, I can take the differentiation dH equal to del H over del P at constant entropy plus del H over del S at constant pressure, and if I compare these two equations, the coefficient of dP and coefficient of ds, then this would be, it is V and this would be T. Now I can consider volume and temperature are measurable. The other thing is this derivative is not measurable, but these two are measurable. If I am able to convert this partial derivative in terms of these two, then the problem will be more simpler. Now the question is how. Here there are three variables: enthalpy, volume and temperature, but here there are two more, one is pressure and entropy. I can use the knowledge of mathematical theories, and if you remember, using expansion rule we can add two more variables in the equation. So I can write this equation as del H over del V at constant temperature using expansion rule. If you remember, the rule expansion is del H over something over del V at constant temperature, del H over something over del V at constant temperature. I am going to introduce two variables P and S. So when I am considering pressure, I should keep entropy constant, del P, and here I am going to consider entropy, then I should keep pressure constant. If I introduce these two values, one is del H over del P at constant entropy, so that would be V, and del H over del V, del P over del V at constant temperature, plus this would be temperature, and this is again del S over del V at constant temperature. This is del P over del V at constant temperature. I can consider this as measurable quantities because I know the equation of state. I can take the differentiation of this equation at constant temperature, but this is not measurable. But do you remember Maxwell relations? This is equal to something. So I am going to write that part. This is equal to del P over del T at constant volume, del P over del T at constant volume, and I can consider this is as measurable because again I can take the partial derivative of this one. Let's derive these two partial derivative using an equation of state. I should write the equation of state is RT upon V plus A upon V square. The first derivative, that is del P over del V at constant temperature. Now I am going to keep temperature constant, and so this would be RT is constant into 1 upon V, that is minus V raised to minus 1, so it should be minus upon V square, and in this case again A is a constant and V raised to minus 2, so minus 2A upon V cube. The second derivative, that is del P over del T at constant volume, so this R upon V would be constant and the derivative of temperature is 1 and there is no temperature term here, so this would be 0. We have received two derivatives. If I insert the value of these two derivatives in this equation, then what would be the final equation? Del H over del V at constant temperature, that is equal to V into del P over del V at constant temperature. So V into RT minus RT upon V square minus 2A upon V cube, and the next one plus T into del P over del T at constant volume, that is R upon V. If I simplify this equation, then it would be minus RT upon V plus minus again 2A upon V square, and this equation would be again RT upon V. This 2 would be cancelled. So the final answer del H over del V at constant temperature, that is minus 2A upon V square. Now this is measurable. Here I can again write H as a function of two variables V and T. I can write dH equal to del H over del V at constant temperature plus del H over del T at constant volume, and this process is an isothermal, so this would be 0 and ultimate equation would be del H over del V at constant temperature dV, and I can insert the value of this one here. So this would be dH equal to minus 2A upon V square dV. If I integrate this equation from H1 to H2 and minus 2A is constant, it is V1, that is 0.04 to 0.1 dV upon V square. If I integrate this equation, minus 2 into A is minus 50, so it would be plus 100 into the integration of this part V raised to minus 2, the integration is V raised to minus 1 upon minus 1. So minus 1 I am writing here, and the equation would be 1 upon 0.1 minus 1 upon 0.04. If I solve this equation, then it would be minus 100 and this would be minus 15. So total is 1500 joule per mole. This would be delta H, but in this problem the number of moles are 3, so it would be 4500 joule. This would be the changes in enthalpy. How to calculate the changes in entropy? In similar way, I should write entropy as unknown quantities, and known parameters are again V and T. So I should calculate the derivative, this one, del S over del V at constant temperature. If I am able to get the value of this derivative, then I can calculate changes in entropy. But this is known. This, using Maxwell relation, this is equal to del P over del T at constant V, and that is equal to R upon V. We have already solved this one using equation of state. The other thing is, I can write entropy as a function of volume and temperature. ds would be del S over del V at constant temperature plus del S over del T at constant volume dt. In this process, the temperature is constant, so this would be 0, and this is equal to del S over del V at constant temperature dV. Now I can insert the value of this from this equation, that is R upon V dV, and if I integrate this equation from S1 to S2, then it would be, R is constant, and this is V1 to V2, that is 0.04 to 0.1, 0.04 to 0.1 dV upon V, and the integration of 1 upon V, that is ln V. So I should write ln 0.1 upon 0.04, and the value of R is 8.314, here delta S. This delta S would be 7.618 joule per mole Kelvin. This is again per mole. If I want to calculate total changes in entropy, then I should multiply this value with number of moles, that is 3. So if you multiply this with 3 moles, then the answer, I am getting the answer is 22.85 joule per mole. I am sorry, I should not write mole because it is joule per Kelvin. This is change in entropy, that is 22.85 joule per Kelvin, and delta H also we got something 4500 joule. Now one more thing I would like to tell you, that if you know delta H, can you calculate delta G? In that case, I am not going to derive in this way, because that equation is famous, delta H minus T delta S. I can put the value of delta H, that is 4500. Temperature, I can, for example, I am considering something 300 Kelvin. So let me write temperature 300 Kelvin, and this is delta S, that is 22.85. If I solve this equation, then delta G would be minus 2355 joule total. So this is total changes in Gibbs free energy. We are getting delta G is negative. What is the significance of negative Gibbs free energy change? If it is positive change, if it is negative change, what will be the significance? Please think critically. Okay. We got delta G is negative. If delta G is negative, the changes in Gibbs free energy is negative, the process is spontaneous. Okay. What do you mean by spontaneous process? The process which occurs without adding any matter or electrical energy, and the process would be spontaneous. It will occur by its own without adding anything. If you add any matter, then it is going to add, but here the condition is we are not going to add anything, as well as we are not going to add any electrical energy, and if process is happening by its own, then we can consider the process is spontaneous. So I can think that it is natural process. Spontaneity is necessary. Spontaneity is necessary but not sufficient condition to occur any process in HUL. This is required, but it is not sufficient condition. Let me take the example. You can convert carbon into graphite at room temperature and pressure, because Gibbs free energy is less than 0 for this process. Gibbs free energy change is negative. So this is spontaneous process, but this is not occurring actually, because you have to add some energy to break carbon-carbon bond. If you add any energy, then it will break this bond. You will have to add something. So spontaneity is not sufficient. Based on spontaneous process or based on delta G less than 0 or greater than 0, you can't tell that the process will occur in HUL or not, because sometimes it is not sufficient. You have to add something. So here in this reaction, if carbon-carbon is converting into graphite, then you require some amount of energy to break this carbon-carbon bond, and that is larger than the free energy change, because delta G is negative. What is the meaning? G2 minus G1, that is delta G. G2, that is the final Gibbs free energy. G1, that is the initial Gibbs free energy. If this is negative, the meaning is G2 is greater than G1. G2 is less than G1, and earlier Gibbs free energy was higher than this one, final Gibbs free energy. So initially the Gibbs free energy was high value, and in final condition the Gibbs free energy was low value. So there is a release of Gibbs free energy, right? Because Gibbs free energy is negative, it is decreasing. So there would be release of Gibbs free energy, and that release of Gibbs free energy in this case is not sufficient, because the energy required to break this bond is larger, is more amount as compared to the release of Gibbs free energy. I have drawn one diagram. What are the different conditions? Delta G, I know that is delta H minus T delta S. How it can be negative? The first condition is if delta H is less than 0, means this is negative, and delta S is greater than 0. This is positive always. In that case, if you take any temperature, this would be always negative, because this is negative and this is positive. So this value, the final answer would be always negative. So at any temperature, this would be the spontaneous process. In case of this one, if delta H is greater than 0, means it is positive, this is positive, and T delta S, in this case delta S I am considering this is also positive, then when this would be negative, this is also positive, this is also positive. So if I am considering high value of temperature, then it would be negative. If I consider high value of temperature, higher value of temperature, then it would be negative. So at high T, this condition will be satisfied and the process would be spontaneous. In this case, the delta H is less than 0, delta G equal to delta S, that is the less than 0, minus T delta S, this is less than 0, so negative, and delta S is also negative. These both are negative, so this term would be actually positive. If you remember, this minus sign, so this would be the positive and this would be the negative. To make it negative, the value of temperature should be low. So at low temperature, this ultimate answer, the ultimate answer of delta G, it will be negative. And for this one, the final condition, that is delta H is greater than 0 and delta S is less than 0. This is greater than 0 and T delta S, this is less than 0. So this is negative. Ultimately this would be positive. So both terms are positive. Delta G is positive. For any value of temperature, this process will not occur. The process will not be spontaneous if delta H is greater than 0 and delta S is less than 0. Here in the case of temperature, we have considered the temperature was 300, but if you consider low temperature, keeping all volume and everything is constant, 0.1 and 0.04, but if you reduce a temperature, then process may not be spontaneous at high value of temperature, because in our case delta H is also positive, delta S is also positive. So this can be possible, the spontaneous process can be possible at high T. So just you can check like temperature, you can keep 100 Kelvin or something and just insert the value and find out delta G, it would be different. Thanks for watching this video. If you like this video, please press the like button and subscribe to my channel. Thank you very much.